Hey everybody, welcome back to the design webinar series on our high performance home in Atlanta. I'm talking to you from the Tiny Lab right now, which is our 200 square foot high performance home. In my opinion, it's one of the most performance tuned homes in the entire world. It happens to be very small. I don't really care about very small. I care about showing people how this stuff works. So now that we have this platform and we've got the television show Home Diagnosis, which is coming out in January of 2019, we have the ability to show people bigger things because we don't have to go to them. So this is you coming to me, showing you how I'm designing the engines of our house. Now the engines, of course, are these things. They are going to be the heating and air portions of this. And moving heat can mean heating, or it can mean cooling. A heat pump moves heat around. It is a more elegant solution than a furnace or a boiler where you're burning something and creating heat out of that. You're just simply using a compression cycle to move heat from outside to inside in the wintertime and from inside to outside in the summertime. So that's a very beautiful process, and it means that you can be highly efficient. We, of course, have that in this house. Exhaust fans. You must have that in a house as well. These are two things that are absolutely required. You cannot have a house that performs in any kind of a way that is controllable without these things. And above and beyond that, every new house, in my opinion and in many people's opinion, needs to have dedicated humidity control. The humidity control that we have depended on in the past has been humidifiers in really leaky houses. And of course, once you air seal a house effectively, you do not need a humidifier. Humidifiers will be a thing of the past. We won't need them anymore. Also, they don't work very well. So there's that. So we will not have a humidifier in this house because the house is going to maintain its humidity in the wintertime. And in the summertime, what we have used classically to dehumidify is the cooling cycle, the air conditioner. And we'll talk about that a little bit, why that's not as dependable as you would think, especially as you get into higher performance homes. Ventilation, very important for anybody who is looking for air quality control. If you have a really old leaky house, you don't need air quality control because you have tons of fresh air coming into your house, tons of conditioned air bleeding to the outside all the time. And that's not high performance, but it is good for air quality. So that can work. But of course, we're not depending on the weather for this. And we have a series on the retrofitting of a one-story ranch on the Home Performance YouTube channel as well. And if you want to learn how to kind of like fix an older home to have the things that we're talking about, that is the series that you would want to see about that. And the last piece of the puzzle is water heating, which we're doing in an interesting way, partly because of this YouTube channel. So here are the goals that we've got. Whenever you are building a house, you're going to want to have goals. How many square feet do I want? How many bedrooms do I want? What do I want the kitchen to be able to do for my wife, who is the cook in our family? How do I want to be surrounded when I am doing dishes, which is my job in the kitchen? Et cetera, et cetera. You get the idea. What price point do I want, right? So all we're doing with this is adding to that list of performance goals the physics and chemistry goals that we're looking for. So here are some of the things that we want out of this house: health and comfort. Pretty simple, right? And the only way you control these is by having a very specific, quantifiable goal, a target in mind. So the health-wise, we've got well-circulated, filtered indoor air. I want to make sure that we don't get dead spots in the house. I want to make sure that the air quality in all rooms is the same, so that there's not some stale rooms in the house, some stale levels in the house. I want to make sure that stale air is exhausted where it's created with local exhaust. And I want to have fresh air supplied. And we're going to put those into the places where we spend the most time. And we want uniform humidity control. And we want it to be around 50%. That's just a good round number for this. And I'll tell you why I picked that number specifically instead of a range. Because most people say, 30 to 50 is a good idea. Comfort-wise, we want to have uniform temperature in all floors and in all rooms. Classically, you walk into anybody's house, the top floor is going to be warmer than the bottom floor. And that's because of stack effect and reverse stack effect in the summertime. So it's those kind of accidental air leakages, heat bleed, all that stuff that ends up kind of shooting your performance in the foot if you don't have control over them. And then water heat, we want it to be quick and controlled. And when I say I want it less than 30 seconds hot, you might think, I'm sure my house does that. Time it. I actually had a job where I was the commissioning authority on an 80-unit retirement building. And my goal, I said, hey, how about water heating contractor? We have all the units in the building getting water that's 120 degrees within 1 minute. By the way, those two things are ridiculous. Number one, 120 degrees is boiling hot. That's going to burn you. Number two, 1 minute was not anywhere within the realm of what this contractor could deliver without working extra hard. They did not know either of these things, which really worries me about contractors who are in charge of installing hot water systems. They don't know what temperature is supposed to come out of the tap. So that was just really worrisome. When I tested it, it came out at 5 minutes. Then they fixed it, and it came out at 14 minutes. Then they spent all day tuning the water heating system. They got it down to within a minute. But I want double that. I want 30 seconds or less. So the targets now. How do we know that we have met these goals for the performance? This is how you do that. Number one, I want all the conditioning airflows. The conditioning airflows are heating and cooling to be within 5% of design. That is a very normal, average error percentage to have in a commercial building. So you'll find contractors who will guarantee within 5% plus or minus of design. Now, how are they guaranteeing that, right? So I'm going to be using our CPS Easy Hood and measuring every single one. And of course, I'm measuring myself. I might have somebody else do this. I'm going to have a contractor who's in charge of the ductwork, so I'm going to be testing somebody else's work at some points, and that can be good. And if you want to hear me talk about the difference between testing your own work and testing somebody else's work, you can do that in other videos on this channel. I want all the ventilation airflows also to be within 5% of design. And that, by the way, is dialable. We're going to change the ventilation airflows depending on what's happening in the house. I want all the house to outside pressures and room-to-room pressures within the house enclosure to be less than 5 pascals at any time with any fan or all fans running. And I'm going to, for sure, test that. That's the point of all of this stuff. Don't put these numbers in your plans or in your details unless you're actually planning to test them and you know someone who can do that for you if it's not you yourself. And by the way, you do not pay the contractor until they have delivered this level of performance, and you put that in the contract. Okay, I want carbon dioxide, particulate matter, and ozone all in safe zones 24 hours a day, 7 days a week. I may be monitoring all of those 24 hours a day, 7 days a week. Or I may be doing spot checks periodically. Either one of those works, as long as you know that things aren't changing on a daily basis. The reason that I have such a finely tuned house is that I know that how it's performing today is how it's going to perform tomorrow and the next day. I might then recheck it 3 days from now just to make sure. But when you have utter control over all of the elements, the heat flow, airflow and pressure, moisture, and air quality in your home, then you don't have to guess what's going to happen. You have predicted what is going on next week, next month, etc. Relative humidity in each home, I want between 30 and 50%. I said that's kind of like the range that people give. In the summertime, it can float between 40 and 60%, blah, blah, blah. I want it to just be 50% all the time. In the wintertime, my wife is from the South, just like I am, but she's more sensitive. And in general, women are more sensitive about air quality than men. She wants it to be moister in the wintertime. Therefore, we're going to go to the top end of that, 50%. In the summertime, if you're not using air conditioning and dehumidification, dedicated dehumidification, then it might float up to 60% plus. We want to keep that down to 50%. So in both seasons, and in the summertime too, my wife, just like many women, will get a dry nose if the air conditioner is drying it out too much. So 50% I think is my dead target. I want it to be right there. All rooms I want to be within 2 degrees of this thermostat set point. And how will I know that I met this? I test it. That's the answer to all of this stuff. And the last thing is water heat. I want it to be 105 degrees, which is the correct answer when you have water coming out on your hand. And we're going to talk about why that makes no sense when I get to the water heating. Actually, I'm going to talk about that right now. 120 degrees is what they say for health codes you want the water to be. But that's the water in your storage tank that's in the basement that's going to lose a lot of its heat by the time it gets up to where you are. So if you're doing instantaneous water heating like we are, the health codes make no sense, and they should actually remake those rules, in my opinion, because that's dumb. If you actually dialed in 120 degrees, you would burn your family. And then if you fell down, slip and fell, you would continue to be burned while you're laying there yelling. So like that's just a nightmare situation. You just don't want that. So 105 degrees is the correct answer for the instantaneous water heat. That's what you want coming out of the spigot. And test that for yourself so you know how hot 105 degrees is within 30 seconds, like I said. So the computer model. First thing you're going to start with is a load calculation. The load calculation is how much heating and cooling is being bled out through the enclosure. So you're going to base this on the 99% hottest and 99% coldest day, not the 100%. And this is really important, and you can double check this very easily. There are databases online where you can find within 1 minute, you could locate the 99%, not days. That's called the design day. That's what everything is built towards. That means that it's going to be oversized 98% of the time. That's okay if you're using the right equipment. And also, you want it for sure to be able to handle that coldest or hottest day, because it can be quite a huge difference between the 98% day and the 100% day. 99% is a good way to do it. So again, heat bleed through the enclosure is where this is based. If you don't know what your enclosure is made out of, it's going to be harder. They're going to have to make a lot of assumptions if you're doing this on an existing home. What is in the walls? What insulation is there? How effective is it? How much air leakage is there? You need testing to do all that stuff. You need blower door testing. You need infrared, all that stuff. Since we're able to dial this in and say, hey, here's how much insulation I want to put in here, and here's exactly how it's going to be put in, because I know, because I put it in my contract for the installer, who is me, that it's going to be 100% perfect, and that's under infrared as well. The big variables that you're talking about are, of course, R value. You're going to need to know what the R value of every assembly is in your house. That's floors, walls, ceilings. Also, windows. What U value, what solar heat gain coefficient are they? And also, potentially, how air leaky are they, right? Because if you're building and you don't know how tight you're aiming for, then you're just kind of guessing with all this stuff. And then also, where the windows are. And I'm going to talk more about that in just a second. Because if you put the windows in the wrong place, you're going to really screw up your heating and cooling load. And then infiltration is the last thing. You need to know what blower door number to put into the design software so that then you can size your heating and cooling equipment. And that's before the house is built. I know what I can deliver because I've already built the Tiny Lab, which is where I'm sitting right now, which is passive house airtight. And the same is going to go for my house. And I'm going to test that and make sure that we actually hit that. It does not model moisture very well. This is because of a weird glitch that happened in the engineering community. ASHRAE, Lou Harriman, let me just say that. L-E-W is his first name, Lou Harriman. Look him up. He's been on the Building Performance podcast a number of times, which is my interview show. Found out in the 90s that the assumptions that they've been making about moisture loads forever, for the whole 20th century, were basically wrong. It is not wettest when it's hottest. So we design generally an air conditioner to perform at 95 degrees outside, like as just a kind of a basic number, let's just say. That dryness or wetness, the amount of actual moisture grains in the air at that point, when you actually look at how weather works, it's actually wetter at 83 degrees than it is at 95 degrees, way up there. So what we should be modeling our moisture control for, our humidity control, is for 83 degree days, which has nothing to do with how hot or cool it is. That's why, in my opinion, and a lot of other people's opinions, there should be a dedicated system for delivering heating and cooling, and there should be a dedicated system for delivering humidity control. And they should not be the same thing. You should not expect one machine to do both things, because that's kind of crazy. They're not the same function at all. Now, here is the breakdown. Remember, if you haven't seen the other webinars, go back and review the basics and also the enclosure. We have two houses in one structure, basically. One is the main house, where all the living and cooking and etc. is going to happen, and sleeping. The other one is the music and dance studio, which is basically a commercial multi-use space. Now, we have two different load calculations that need to happen at that point. You could do what's called a block load, which is essentially what this big number is a block load on both of those. If I was to do a block load on the whole house, I would find out that my entire house needs only 1.5 tons of cooling, for example. So in the main house, I have 13,000 BTUs needed for cooling. That's a little over 1 ton of air conditioning. Most manufacturers do not make a 1 ton split system air conditioner. So now I'm oversizing already. You can see that the walls suck up a lot of the heat bleed in the wintertime, in heating season. And then the glazing, which is the windows. That's the glass portion of the windows generally. The doors are a little bit, the ceilings are some, and the floors are some. You do not see infiltration on this list. That is a cool thing because the infiltration is basically nothing. It's rounding down at that point in this graph. And that's because I modeled it to be 0.6 air changes per hour at 50. Don't worry about what that means if you don't know. And in cooling season, you can see that the glazing, the windows, are the big deal that forces us to air condition. That's, again, where the window thing really comes in handy. And then the walls, obviously, are a big deal. Walls are a big deal in this house because there are more wall surfaces than there are anything else. So that's why they'll end up looking the way that they do. Now, in the studio, you see that we're missing something big. We have walls. We've got ceilings. We have internal gains in the summertime. And that's because there's going to be music equipment and computers and lights and things like that in there. But there's no glazing, and that's because I intentionally designed no windows into the studio. We're located next to the world's busiest airport, and by the way, it's been the busiest number of people-wise, number of passengers who come through there. It's 278,000 a day come through my town and go to the airport. And it's been that way for about 20 years. It's been the busiest airport in the world. So I don't want the sound of the planes to be coming into my music studio. I want to be able to have a nice, polite, civilized dance party in there and not have the roaring of planes going through. And by the way, you've seen videos outside here. It's not that noisy in general. Now, the window placement leads to something called adequate exposure diversity. This is RightSoft, which is one of the two big load calculation softwares. You have to use a software to do this load calculation correctly. You cannot do it on paper unless you're in one of like a few tiny places in the US. So you're using the software and you're putting in all the stuff about the enclosure, and then that software is going to tell you, oh, here's the amount of heat bleed out through all this stuff and through air leakage, and based on the sun rising and setting at different angles throughout the year. And we can model, the graph you see on the left is the adequate exposure diversity, AED, for the main house. And you can see that the green line is the average exposure diversity. That is the average amount of BTUs that I'm going to need to subtract from the house that's being added by the sun as it goes across the sky from 8 a.m. until 20 o'clock, which is 8 o'clock at night, right? So sunrise to sunset. You can see that the sun is having a more extreme effect on my indoor spaces at 17, which is 5 o'clock in the afternoon. That's really what you're designing an air conditioner for, is that 4 to 6 p.m. when you come home from work, sun's beaming in at low in the sky, and you're cooking, and everybody gets home at the same time. So we're adding our bodies to that warmth, and we're turning on lights, and we're turning on appliances, computers, maybe we have the TV on. All that stuff kind of comes to a head at about 4 to 6 p.m. on a Saturday afternoon. You can see that I am not tapping out the max adequate exposure diversity. So the max would be about 8,600 BTUs per hour. And I'm just coming in on the inside of that. Now, if I had no windows, like on the right, you can see that the sun makes no difference at all day long. So I don't have to worry about that. This is where you start getting into these arguments about like, oh, we've got a big west wall because I'm on Lake Tahoe and I want all my windows. I want that to be a solid window wall. You're going to really screw it up. You're going to end up having to install an air conditioner that is twice as big as it should have been just because you put the windows in the wrong place. So this is a really important thing to model for as well. Now, every house should have what's called a service chase. This is a place to put things like wires, ducts, light tubes, plumbing, things like that. Because the main problem with all this stuff is once you start making modifications, you're going to have to punch into all kinds of different weird little cavities in the closet wall and the bedroom wall in order to get at the services, the cables and the electrical and plumbing and all that stuff that you're scattering all over the house. If I have them all through one specific chute that maybe has a removable panel on it, right? So instead of drywall, I could put pretty plywood that's finished nicely or painted just like the walls, and it's put on there with screws, and I can take that entire wall off and get at everything. That's very helpful. So we have that, and it's dead in the center of our house. It runs through the bathrooms that are stacked on top of each other. So you can see it there on the first floor, and that's in the master closet. It takes up some of that room. And then on the second floor, it comes up through the second floor bathroom. And you will see all the stuff that goes in there if you follow the build, which is going to also be on this channel, the Home Performance channel. So make sure you're subscribed for that. Okay, ductwork. Here's the first floor plan. And the ductwork basic characteristics I want are round. Round duct is better than rectangular duct. So I'm going to try and use round all the time. And I have this service chase, which goes up through the house, and I can use round there. I can also do what's called rectangular plenum, which is like a trunk, like the trunk of the tree, and then branch off from that with round. That's gonna, you want to have basically what's called turning vanes, which are little devices inside the ductwork that kind of will help turn and curve the air to make it go where you want to go. But all this stuff is designable. So if you're like, you know what, I have only enough room to do rectangular, then you can model for that. And you can say, well, we want to use these parts and these components and these devices in the airflow to make sure that it goes where we want. So I'm going to be using round, though, which is good. Rigid metal is going to perform better than flex duct. So we're just going to do that. 3 feet, though, from the terminal, from the vent face, we're going to switch over to flexible. And that is to to decouple, basically, the face of the grill from the vibration that's coming down the duct, which is rigid again, which is connected to my air handler. So that is a noise canceling element. And so we're going to do that as well. That's generally a common practice. It's going to be sealed because I do not want the plumbing for my air leaking out inside of my service chase or inside of my crawl space or inside of my little tiny attic on top of the second floor bathroom. But it's not going to be insulated because it doesn't matter. I have an enclosure that is so hardcore, and the air is going to be moving at different rates than at a conventional house's rates. I have decided that we're just not worrying about that. So that's something that is like, oh, if you wanted to be really efficient, you could do that. And I'm just deciding not worth it. For the amount of space that I'm going to save inside my service chase, for taking away that inch or two of insulation on the outside, it's worth it. Now here is the crawl space on the left. You can see that we need heating and cooling down there. And this number in the crawl studio section is 57 CFM. That's the highest number, whether it's cooling or heating. And likewise, in the main space, I have both a supply and a return, 135 each. And that's because the crawl studio is actually not going to receive that. It's going to have an opening into the crawl from the studio above. So I'm just going to make sure that that stays open most of the time so that we equalize the temperature and relative humidity between those two spaces. And I'll close it when we need to, if we're having a dance party, whatever. But that's one of the options you can have, is you can open the crawl to the space. And just a reminder, these crawl spaces will resemble exactly very nice, well-performing basement spaces that are unfinished. They're not going to look like what you think of as a crawl space. You can see that in the other design video. Now upstairs, in the kids' bedroom, you can see that we've got 83 CFM coming out in the kids' bedroom and 64 CFM coming out in the guest bedroom. Why is that? Those two bedrooms are exactly the same size. They have the same number of windows and the same number of doors. Why would that be? And it's because of facing. The kids' bed on the top faces south. That's which direction those windows face. And the guest bed faces north. So cooling is the main thing that we're dealing with there. We need more cooling in the kids' bedroom because that sun is going to beam in through those windows in a different way. So again, this is why you just don't do a block load. Block load is dumb. If you have to, and if you're just not willing to spend the money, or if you're dealing with an existing duct system that you can't change, then you do a block load. And you say, okay, well, here's how much heating and cooling we need for the whole house, and then you just split it up proportionally. But I wouldn't know that the kids' bed needed 83 and the guest bed needed 64, and how many BTUs that correlates with, if I didn't do this room-by-room calculation. Okay, now, we did the load calculation, and I used RightSoft software for that. That's a dedicated calculation. I am also using what HERS raters use, called REM. to model, residential energy modeling, I think is what it stands for, to model the energy flow within the house. And this is a different thing because we can essentially do value comparison, cost effectiveness comparison with the energy model software. A lot simpler than trying to go through and do it with the RightSoft. So I can break out what my heating, cooling, water heating, lights and appliances, photovoltaics, and service charges are going to cost me or are going to benefit me in the case of PV per month and per year. And you can see that all of my utilities should come in at $1,500 or less per year. Now I can tune that, and we already talked about this in the last video, but I choose not to because it just doesn't make sense for me to spend more money trying to save, like let's just say $500 a year on this, times 30 for my mortgage is not going to give me what I need for the amount of upfront cost that it's going to cost me. And I know how much it's going to cost because I'm the one who's doing all the budgeting. I'm the one who's doing all the scheduling and picking the supplies and the materials. So, and doing all the work with my family. So here's what you can do now is to figure out, first of all, whether you have calibrated correctly your energy model with your load calc. They should come in about the same numbers. And in this case, they do. And I can also kind of break out and make it a little bit more visual and see the information in different ways, whatever works for you. If you like pie graphs, you like pie charts or bar charts or whatever it is, you can get them. So I can see that I'm not designing solar in here, and I will get to that at the end. But my above grade walls be an example. Above grade walls, you can see, are most of the heat suck on the left here in heating season. It's the green bar. My ceilings are a little bit less of a suck. Now that's interesting because there is proportionally about the same amount of ceilings and walls. But I will just remind you from the last webinar, we have a ceiling sandwich that is not going to be, not only is it not going to have exterior insulation like the walls are, but it's also not going to be completely filled with insulation. It's going to only have 8 inches of insulation in a 12-inch cavity, or like 10 inches of insulation in a 14-inch cavity. I can't remember which it is. And that is because I have value engineered this. If I was to take that up and fill the entire cavity, which is going to cost more because I'm going to have to add more insulation, and also I might add some on the outside because we've got some on the walls, it's going to not make any difference because I've got the numbers right here in the energy model. That's what the energy model is beautiful for, is helping to make decisions that are based in science, not are based in, oh, well, we've got it outside the walls, we might as well have it outside the roof as well. And you can see in the cooling season on the right, the very, very, very right bar that you see over there is salmon colored, if you like your salmon colors. It's huge. And that's because we're going to have a lot of internal gains. That's the refrigerator running, dumping heat into the space. We've got the water heaters that are giving off a little bit of waste heat. We've got the interior computers. We've got the television. We've got the lights, even though they're all LEDs. So this is all stuff that you want to kind of model for and make sure that you're prepped to be able to cool for the stuff that you're going to be doing in the house as well. And if you plan on having a server farm in your house at some point, you need to model that. Just to be prepared that that is something that's going to happen. Now you can see a couple things on this chart. This is also from the energy model. Number one, infiltration is modeled up there. And you can see that I've got 18.7 total kilobTUs per hour needed of heating in the entire house. Not just the main house, but the whole house is what I did the energy model on. 1.1 of that, almost like 5 to 10%, of the entire need for heat is based on infiltration. That is not coming from air leakage. That is coming from ventilation, which is required. Now, again, remember, this is not energy efficient. Ventilation is for controlling the chemistry of your house, and also the humidity and the temperature, stuff like that. But the fresh air need is very important. And home chem taught us that you really want to flush out that indoor space because it gets really polluted in there really fast, no matter where you live in the world. So I am intentionally bringing in fresh air, driving down my efficiency on my house so that I can have fresh air. And that is not something to feel bad about. That's something to feel good about. You definitely need to make up for the heat that's lost from exhausting the stale air. Second thing to notice is that I have a heating and cooling system. Now, when you start an energy model, you're just going to plug in a number. And I put in, just for a joke, a 41 kilobTU per hour furnace and a 3-ton air conditioner, because that's what I see on a lot of houses. They're going to be 3,000 square feet. What it turns out I need, based on the energy model, and again, I want to calibrate this with the load calc, is 18.7 kilobTUs per hour of heat. They do not make a furnace that size, so I must use a heat pump at this point, or an electric toaster, basically, electric resistance heat, which is a terrible way to heat. And I only have less than 1.5 tons of air conditioning needed for the whole house, just as a reminder, not just the main house. So now, again, they don't make an air conditioner that's less than 1.5 tons, most manufacturers. So I'm still like really having to deal with that. That's another reason why I'm not adding more insulation to this house, because frankly, I'm tapped out. I'm dragging the bottom of where people manufacture heating and cooling equipment. So to get to the conditioning, right, we need space heating and space cooling. Mitsubishi is where I go for that. That's what's installed here on the Tiny Lab. And just as a demonstration, that is my ductless mini split that is the same exact model that's going to go into the studio. And it is running right now. See that green light? See that little twisty infrared eye? That is what's beautiful. I've been giving you a video, and this the heating unit has been running the whole time I've been talking. You can't hear it. I'm sitting 2 feet away from it. That's what's beautiful about Mitsubishis. They do not joke around. Is it going to cost more? Yes. You pay for what you get. If you want something cheap, don't watch any of my videos, ever. I'm not going to point you to cheap stuff. I'm going to point you to the best stuff. So, first thing is we've got the main house. We're going to have a split system, like a normal ducted heat pump system, like anybody would have in their house. And that is because, number one, it's the best application. And number two, there's nothing wrong with ducts if you do them right. That means they need to be sealed properly, they need to be designed properly, they need to be installed the way that they were designed, which also means that I, as the builder, now need to make sure that there's room to put the ducts exactly where the duct design says they need to go. We're going to have a 1.5 ton air conditioner, which is kind of the same unit, is going to also do the heating. Now, heating in Mitsubishi units, and I think in most, is going to be more. You're going to be able to deliver more heat than cool. So 23 kilobTU split system on the heating side. The efficiency numbers are right there for you. One number that's really important to me is the sound. 33 decibels is very quiet. This thing that's running right here is what we're going to install in the studio. It's the exact same piece of machinery, and it's going to go, instead of a 200 square foot house, it's going to go into an 800 square foot studio. So it's going to handle the same exact need. And by the way, this thing can run off grid. I run my entire house, just as a reminder, on 15 amps, 120 volts. I can plug this entire house, including that thing, into one outlet in your house. That's how efficient it is. So just as a reminder, having an oversized piece of equipment, as long as it's running on an inverter that can really dial down and give you only what you need, is a beautiful thing. This one is 33 SEER, and it's running 47 decibels right now. And that's this thing that we're going to install, the split system, is even quieter than what I'm talking next to. That's important. And 3-speed on the inside of the house, instead of it endlessly variable, which is what we've got here with this mini split, at 47 decibels. But you can see this one is wildly more efficient than the split system. And I don't know why that is. I'm not a researcher, and I'm not a scientist on all that stuff. But I would say that 17.6 SEER is a good number. Like, yay, that's great. Just as a reminder, I'm not building this house to be energy efficient. Energy efficiency is a byproduct that we will get out of this house. But that is not my goal. My goal, I already said, is health and comfort. Okay. Now, Fantech. Next thing you're going to need in any house, in addition to your heating and cooling system, which we have the best one of, is an exhaust system. You're going to need exhausts everywhere you create air that you don't want sticking around in the house. That is bathrooms and kitchens. Now, just as a reminder, you don't want the fart fan mentality. You don't stick your exhaust fan in your bathroom over the toilet. That's not what it's for. You stick it so that it'll grab what's going on in the toilet. That's a nice byproduct, but it's mostly in charge of taking the humidity out of the room. So we've got the kitchen range hood with a silencer on it. Now you can see the kitchen range hood right underneath my face. It's called an insert, and that means that I can design the cabinet, the hood, or what's called the sump, if you want to be really technically correct about it, into a bowl or box shape, just like I said in the most recent video, like from the last week or so, on Broan. If you want to search it on the channel, it's called Kitchen Range Hood Buy-In Guide or something like that. And that explains exactly all the features that a kitchen exhaust hood should have in order for it to perform the way that you want it to. The silencer is good because it means that I'm going to be able to put this inline fan downstream and have a silencer between the hood here and the fan so that it should make virtually no sound at all. That can be a danger if you don't control it the right way. So we're actually going to install a heat-activated control on this so that when it senses that somebody has turned on a burner, it's going to turn on automatically. I don't have to touch it. And I'm going to dial in exactly what number I want to be able to exhaust all the air, whether I'm using one or a number of the burners. We've got a 5-burner setup, by the way. We already have it because Grace has been doing a great job of keeping the costs low by finding people who are remodeling their kitchens and grabbing their stuff. So I can dial it later if I want to, because there will be a dial there. But also, it's just going to be automatic and plug and play. I don't have to worry about it. Now, active, conditioned, filtered makeup air. That's beautiful. If you see that video of the Broan system that we have here in the Tiny Lab, what we have there is a passive makeup air. It's just a hole in the wall that's got a damper that's mechanically activated. And when it senses that the kitchen exhaust hood turns on, it opens up that hole and allows fresh air to come in. If I was to try and really control the pressure in here, and by the way, here on low, we get down to negative 10 pascals. I already said I want it to be 5 pascals only. The theory at Fantech is if you're going to use a big fan to suck air out of a house, and then you want makeup air, the smartest thing to do is to actually use a fan to then push air into the house. And then you've got really responsive, really accurate replacement. So I'm literally doing a 1-for-1. If I just suck on the house and then I open a hole in the wall, in order to get true equalization of the pressure, I need to have a ton of holes. I might need to have like 10-inch holes if I've got a big enough fan. And even then, now what's happening with all that stuff? Like, number one, it's not getting filtered. It's just coming straight into my house. There's going to be a bug filter on it. That's about it. And it might not have a heater on it, which is what this thing also can have. So I can have air come in that is not going to make my feet cold, and it's not going to screw up my humidity levels and screw up my particulate levels and my ozone levels, all that stuff. So the filtration is really good on that. Radon mitigation system. I'm going to talk more about this in just a second, but that's the inline fan that you can see over here that looks like a box. And the dryer booster. I was going to put the dryer on an outside wall, which would be smart. And anybody who's thinking about doing that should do that. But we had an architect named Jody Lamorgiddens from LG Squared redesign the house to make it more beautiful and to make it more like livable, which we don't know anything about. We designed this thing for performance. So she tweaked the house and redesigned it and moved the laundry system, which is a better place. Like, we're absolutely taking all of her suggestions and we're moving ahead with her design. But the dryer now is in the middle of the house, and I need it to get outside. So I'm going to have a booster fan on this to make sure that that humidity gets all the way outside, that it's not just getting up there and then having this lint deposit and forming the dangerous situation that results in dryer fires. So, radon. Here's what's cool. Number one, do we care about radon? Sure. Yeah, we care about radon. Anybody who goes on my one video about radon tracking with that Corentium radon monitor and says, radon is a scam, they're just trying to scare you. Like, everybody's trying to scare you about everything. Somebody who's yelling at me on my YouTube channel is trying to scare me about something too. So for sure, there's all propaganda. I don't really care about whether radon is or is not proven to be bad for my family. It's a gas that comes from radioactive stuff underground. I don't want my children breathing it. I don't care whether it's really unhealthy or just a little unhealthy or it's a whatever. I'm not taking the chance. So, number one, we are having a radon mitigation system to take care of radon, yes. It's going to be an inline fan from Fantech. It might be that box that I showed you. In general, you want the fan to be outside the house because if it leaks, you don't want it blowing the radon-tainted air inside the enclosure. So that's the quickest way to just get it right outside, go outside, have the fan there, go up through the roof, and exhaust it out above the house. It's going to suck on the Formadrain and the 6 inches of 57 stone that we're going to have underneath the slab, which is also underneath the Pango wrap, which is also underneath the 2 inches of rock wool insulation. So It's gonna work for that, for sure. But also, that's not even the coolest thing. Getting rid of radon is the lamest thing that we're going to do with this radon mitigation system. Joe Nagin is who you need to talk to if you are really serious about learning more about this. But you can learn more about this here on this video, because I will take what he told me, which is that it also evaporates moisture. Think about your drain tile. And this is the forma drain that's going around the outside of my footing, on the inside and the outside. The footing of a house is flat. So if you're going to use PVC drain tile, clay drain tile, or forma drain, it's going to be flat. You're not going to have a drain that's sloped like this, that's going to take water and shoot it out this way. The whole thing, the point, is for it to go around the entirety of the outside of the house, which is flat. So now I have this flat tile that might be filled up with water, which is hopefully that's what it does, is it fills up with water and then tries to take that water out. When it's not doing that, and there's just a little bit of water sitting in it, this fan is going to evaporate that. That has a number of consequences. Number one is out your house, because it turns out that some of the moisture that's coming into your house is coming in through the footing, absorbing moisture, and capillary bringing that moisture up into the space and then evaporating it into the house. So I'm going to stop that from happening, which means I will dry my house. In the summertime, that's very useful. In the wintertime, I'm already hanging on to the humidity, remember, with my airtight house. It also is going to, because we're not evaporating the water from the footing, from the bottom of the foundation wall where it meets the slab anymore, that's where it's going to come, collect, and evaporate into the air. It's going to warm that, because when you sweat and evaporate sweat off of you, it cools your skin. Exact same thing is happening here. So when you see that you've got a little bit of mildew forming at the bottom edge of where the foundation wall meets with the slab, that's because of what I'm describing right now. We're going to stop that from happening, which is going to warm the foundation wall and is going to then prevent that condensation, which is going to form that little mildew. So so many interesting things happen when you use this active radon mitigation system, the least cool of which is radon goes out. Yeah, that's fine. So yes, that will happen. Okay, Ultra-Aire Dehumidifiers, the dedicated dehumidification system that we have. In this house, I have a dehumidifier that's a desiccant dehumidifier, and it also might turn on at some point, and it's very quiet. I also bought, a non-compressor one for this house because it's so small. That's quiet, desiccant. Ultra-Aire is not a desiccant. These are run on compressors, which is more high efficiency for sure, because the compression cycle is the same thing that makes a heat pump more efficient than a furnace. So in the main house, we're going to hang in the crawl space this XT105. Now the XT105 has a cool feature that I'll mention in a second, which is super nerdy. But it runs drying for up to 3,000 square feet. Now, in the main house, I have 2,200 square feet. But I also have this crawl space, which doesn't really count into my conditioned floor area calculation. So that's why we like the 105, is that it can do up to 3,000 square feet, which does include, in our case, then, the crawl space. It can do 105 pints per day. This is how you judge a dehumidifier. Not based on, the humidity level it can maintain or anything like that. You want to know how many pints per day can this thing take out. So it's going to take out 105 pints per day. It only runs 530 watts, which might sound like a lot, but it's not a lot. Like a hairdryer being 1,000 watts, 1 kilowatt or more. MERV 13 filter, also very important. I like all that filtration. Like, just let's give stuff, the chemicals and the particles in the house, stuff to stick to at every point. Every option is great. Now the XT also has the benefit of, and you're going to have to see this to really understand what it is, but there is a heat exchanger inside of this thing, like an ERV core. And I mentioned this in our crash course on ventilation video. And if you search ventilation, you can see this table of like 5 different ventilation options, and Ultra-Aire is one of those options. Now, this thing has an ERV core, which is basically, they don't like me calling it an ERV core. That's what it looks like, though. It's a heat exchanger that's a square that's got 2 streams of air, right? So they use this heat exchanger to change the dynamic of the pre and post coil air temperature, so that they can change the dew point, and they can hit the dew point faster on that coil and wring even more water out of it than if you just took the air that's right next to my face, passed it over a cold coil, and stole a lot of the moisture out of it, and then you had some cold air come out. They actually are going to emphasize that process and try and make it even more likely that they get as much water as possible. I just think that's kind of cool. In the studio, we have a different model. We've got their in-wall model. Now, this thing does not have a heat exchanger. It does not. It's not set up to do ventilation also, which this thing can do. But of course, we've got the Fantech system that I'm going to talk about in a minute for that. The MG33 can do up to 1,200 square feet. Again, the crawl space is part of this equation. So my studio is 800 square feet. Underneath it, the crawl space is another, let's just say, 400 if you were measuring 8-foot walls. But it's not. Of course, it's 4-foot walls. So this is going to handle all of that. And I don't expect a lot of moisture coming up for a bunch of reasons I've already gotten into from the crawl space. But just in case it does, we've got the option. Now, this thing pumps 33 pints per day. And it's pretty efficient. So this thing only needs 120 volts or 110 volts, right? And it's really quiet. Again, 46 decibels is quieter than this ductless mini split that I've got over my head. I like that. I'm, of course, going to dial it down when I'm recording, but I won't have to worry about that. Now, ventilation system. This is where we're starting to get into extra credit. Now, it's really not extra credit, but for a lot of people, they'll say, oh, well, I'll just open windows, or I'll just run my bath fan all the time, and then I expect that the air is going to come into the house to replace what I'm leaving. You can do that. That is not high quality, and that's not high performance. So what we're doing, of course, is everything the best way. I want this to be the best house you've ever seen. The Fantech system we're going to use, number one, is a HEPA filtration unit. This is something that you can either have standalone, or you can duct in and connect it to the return and the supply duct so that you're filtering at least some of the air that's going through your system all the time. HEPA means that you are taking care of a bunch of the particles that you would be worried about. Now, because I know home chem, I know that 300 nanometers is actually pretty big. These are some boulder-sized particles. When you run a toaster, you're creating particles that are smaller than that. They are not going to get caught by this thing. That's okay, though, because I have a way to do that. We're going to actually have a shelf on our stovetop. On the backsplash, there's going to be a shelf where the toaster lives. And every time we make toast, right, when the heat gets created, this thing is going to kick on and we're going to be exhausting even the air we're creating from toast. If you have a George Foreman grill, also, you want to make sure that that thing lives on the stove, or you have got a place for putting it on the stove when you use it, because that way you can still use your kitchen exhaust, still have all those particles go outside, and the chemicals. We haven't talked about that, but we won't worry about it. The other thing is the counterflow ERV. ERV stands for Enthalpy Recovery Ventilator. You can think of it as an equalizing ventilator. I've talked about this ad nauseum. I'm sure if you've watched a lot of this channel, you know what an ERV is. This thing is going to make sure that we have brought in an equal amount of fresh air for the stale air that's going out. Now, all of the bathrooms are going to be hooked up to this so that I'm exhausting 24/7 out of the bathrooms at a static level. Additionally, we're going to be supplying air into the bedrooms, the 3 bedrooms, kids, guest, and master. And so we've got an equal exchange there. And inside that box, it's going to be at high efficiency, pretty high. That's what the counterflow core is for. And I'll go into that when we actually have it in hand. Or if you can come see me at IBS, I'll be at the Builder Show in Las Vegas in February presenting for Fantech. So come, feel free to say hi. When we put that in, it's going to rub the 2 streams of air together, make them the same temperature, same relative humidity. That's what it's trying to do anyway. Okay, and the last piece of the entire engine puzzle is the water heating. Chronomite is this company that I found that makes fantastic point-of-use water heaters. Now, we're going to have 5 of these in the house. You can see the red X's down here. This is what they look like. They're microprocessor controlled, and they're totally made in the US. That's important to me because a lot of the things that are going into this house are not made in the US. They are made in Europe, and it's because a lot of people in the US do not care about anything that I'm talking about right now. They will once they see what the alternative is and they know what's possible with this stuff, right? But for right now, manufacturers just don't see a benefit in manufacturing stuff in the States. So when we do manufacture in the States, I like to make sure that we make a big deal about it. So these things, microprocessor controlled, means that it takes 120 readings a second or something insane like that and makes sure that it's delivering the right temperature at all points. So if the incoming air water stream changes temperature, it'll know and it'll adjust for that. If we turn on another fixture somewhere on that same system, it'll say, oh, temperature's dropping, I need to kick up. And so it'll like immediately react. That I really like, all that responsiveness and performance. They're very small. This thing is like literally this big. So it can go underneath the cabinets where the sink is. And we've got a couple different kinds. So we've got 4 kinds that we're going to put in. We've got the smallest one that they make for residential, which is 3.6 kilowatts when you are using it on high. And the biggest one that they make also is going to go in here. The biggest one is going to serve the master bathroom, which, as you can see, is also coupled with the laundry room. So we've got the clothes washer, we've got the shower, we've got the bathtub, and we've got 2 sinks within that master suite, all powered by one point-of-use instantaneous electric water heater. It's going to require 30 kilowatts. That means I'm going to have basically 2 or 3, I think it's 3 circuits dedicated just to this water heater. Electricity is the worst way to heat something. When you're just doing electric resistance heat, yes. But also, this is super smart because I'm only heating what I need. It comes out immediately. In fact, it's not even, the 30-second thing is kind of a joke. It's going to come out within like 5 or 10 seconds. It'll be at full temperature. So I'm not wasting a bunch of water now, turning on the water and then just hanging out and waiting while it all goes down the drain. I think water efficiency is something we all are going to have to really pay attention to in the future. Again, we're not talking about efficiency in this video, but that's just a side note. So yeah, there's going to be a serious dedication of amperage. I think it's going to be 3 circuits that are each 40 amps a piece or 50 amps a piece. I'm not sure, but it's pretty serious. And lastly, we have, they're going to activate at really low levels. So we've got 0.35 gallons per minute. Hang on one second. Let me grab my power. .35 gallons per minute means that I can just turn on the hot water on low, or I can have a very mild mix of hot and cold. My laptop was about to die, sorry. And that's good. The one that I have in the Tiny Lab here, which I've had problems with, because it has this feature, is that it turns on at half a gallon per minute. 0.5 gallons per minute is when it says, oh, you want hot water, I get it. So you can't just go and turn on a little bit. 0.35 gallons per minute is pretty low, so I don't think you're going to find anything that's much lower than that. Temperature control, field settable temperature control. That means there's literally a dial that I can say, ooh, I want it a little bit warmer, a little colder. I love that. Anything with performance feedback where I can say, ooh, I don't like that, I want to adjust it right now, right while I'm looking at this thing, that's what I like. Okay, so last video in the series, which is coming up in a few days, is the bells and whistles. The bells and whistles are all the stuff that we're doing towards home chem control. This, by the way, is that ventilation video that I was making mention to. If you want to see more about the ventilation, both the exhaust, the whole house fresh air ventilation, and the dehumidification, you can see in that video a little bit more in depth. So home chem, if you haven't seen the 35 videos that we produced from that experiment in Texas this year that was funded by the Sloan Foundation, it's an independent thing that was all about kind of founding this groundswell in this study that has been around for decades, but they haven't been able to go very far with it because they haven't had the tools. So this was a really exciting year for that. The wall materials, what are the interior walls going to be made out of? This is going to be interesting for you, I think. Ozone-killing paints, the non-reactive sealants, the outdoor spaces that we've got designed, and also the solar prep, which I said we're going to get into in this one, and we'll just leave it for the bells and whistles because it, frankly, is a bell and whistle. So please tune in for that. Make sure you're subscribed so you get notified about all that stuff. Now, don't forget that we've got the television show coming out. January 2nd is when it gets released. It'll probably be on Saturday afternoons in most places around the country. So please do find out and go ahead and ask. If you belong to PBS or you watch PBS, call them and say, hey, are you guys going to be programming this thing? We're getting reports every week about the stations that are programming this. You can see it at homediagnosis.tv. Now, these are the amazing sponsors that, again, have put their money where their mouth is, and they made this television series possible. There has never been a television series about building science or home performance before. So these companies, in my opinion, are the heroes of this story. If you want to know more about this on a professional level, I have a Mastermind course. That also is going to open up for open enrollment in January. to celebrate the release of the show. It's going to be a little cheaper because we're not all doing it at the same time. I'm not going to have office hours every week. It's just going to be more of like a plug and play. You can learn what you want when you want. And so it's the same high quality. It's just not timed anymore, and you're not kind of networking with a bunch of other people who are doing it at the same time. And that, by the way, is at homeperformance.training, or you can see it at the main website, Building Performance Workshop. We've got over 300 videos. This keeps getting bigger all the time. By the time we're done with this build, there's probably going to be 500 videos on here, I swear. So please do make sure that you are subscribed to this channel, because this is, if you like it, if you comment, all that stuff helps us to show that we're giving value, so that the television stations take us seriously, so that people who are in media say, oh, I want to write a story about home performance. So all that stuff really matters, and I appreciate it when people review, comment, like, and especially when they subscribe. You can listen to me ask dumb questions of people who are amazing at the Building Performance Podcast. That is on hiatus right now. I don't really see that picking up soon because I'm just so busy with all the rest of the stuff. But it's free, and you can get it wherever you get the rest of your podcasts. So thanks very much for watching. If you have questions, if you have comments, I do personally respond to every single thing that happens on this YouTube channel, so please do feel free to reach out. Tune in next time.